Welcome to the YouTube channel. In this video we will study Lecture 5 of Class 12 Chapter, Current Electricity for Board, NEET, CET and JEE. If you have any doubts please comment or join the Telegram channel. Lecture 1, 2, 3 and 4 video link is given in description. And don't forget to subscribe the channel. Let's start. Obtain the expression for equivalent EMF and internal resistance of two cells connected in series. Or two cells of different EMFs and different internal resistance are connected in series. Find the expression for equivalent EMF and internal resistance of the combination. Consider two cells in series. Let P and Q are two cells connected in series. E1 and E2 are EMF of two cells. R1 and R2 is equal to internal resistances of two cells. I is equal to current sent by two cells. E is equal to equivalent EMF. Let RS is equal to equivalent internal resistance. VA is equal to potential at a point A. VB is equal to potential at a point B. VC is equal to potential at a point C. Potential difference between A and B is VAB is equal to V minus VB is equal to E1 minus I, R1. Because B is equal to E minus IR. Potential difference between B and C is VBC is equal to VB minus VC is equal to E2 minus IR2. The potential difference between A and C of the combination is VAC is equal to VA minus VC. That is equal to VA minus VB plus VB minus VC. Now substitute values, we get E1 minus IR1 plus E2 minus IR2. That is equal to E1 plus E2 minus IR1 minus IR2. Therefore, VAC is equal to E1 plus E2 minus I into R1 plus R2. Mark as equation 1. But VAC is equal to EMF of equivalent cell. VAC is equal to ES minus IRS. Mark as equation 2. On comparing equation 1 and 2, ES is equal to E1 plus E2. This is the expression for equivalent EMF. RS is equal to R1 plus R2. This is the expression for equivalent internal resistance. Note 1. For n cells in series, ES is equal to E1 plus E2 plus E3 plus so on up to En. And RS is equal to R1 plus R2 plus R3 plus so on up to Rn. 2. If negative terminal of first cell is connected to negative of second cell, then ES is equal to E1 minus E2. And RS is equal to R1 plus R2. Next, obtain the expression for equivalent EMF and equivalent internal resistance of two cells connected in parallel. Consider two cells in parallel. Let E1 and E2 are EMFs of two cells. R1 and R2 are internal resistances of two cells. EP is equal to equivalent EMF. RP is equal to equivalent resistance. V is equal to potential difference across each cell. I1 is equal to current flows from first cell. I2 is equal to current flows from second cell. I is equal to total current in the combination. In parallel, I is equal to I1 plus I2. Mark as equation 1. We know that V is equal to E minus IR. Therefore, IR is equal to E minus V. Or, I is equal to E minus V by R. For first cell, I1 is equal to E1 minus V by R1. For second cell, I2 is equal to E2 minus V by R2. I is equal to E1 minus V by R1 plus E2 minus V by R2. This can be written as I is equal to E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. Therefore, I is equal to E1 by R1 plus E2 by R2 minus V into bracket 1 by R1 plus 1 by R2. Mark as equation 2. But for equivalent cell, I is equal to EP minus V by RP. Therefore, I is equal to EP by RP minus V into bracket 1 by RP. Mark as equation 3. Now compare equation 3 and 4, we get EP by RP is equal to E1 by R1 plus E2 by R2. And 1 by RP is equal to 1 by R1 plus 1 by R2. This is the expression for equivalent EMF and internal resistance in parallel. Note 1. Expression for N cells in parallel. EP by RP is equal to E1 by R1 plus E2 by R2 plus E3 by R3 plus so on, up to En by Rn. And 1 by RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on, up to 1 by Rn. 2. If negative terminal of second cell is connected to positive terminal of first cell, then E2 tends to minus E2. That is, EP by RP is equal to E1 by R1 minus E2 by R2. And 1 by RP is equal to 1 by R1 plus 1 by R2. Let's look some definitions. 1. Electrical network. The different combinations of resistors and cells is called electrical network or circuit. 2. Node. The point in an electrical network at which the current finds more than two branches is called node or junction. 3. Mesh. The closed path for the flow of current in the circuit is called mesh or loop. Next, electrical power. The energy dissipated per unit time is called electrical power. Formula is electric power is equal to energy dissipated by time taken. Here, energy dissipated is equal to loss of kinetic energy. That is, delta W is equal to IV delta T. Now substituting we get, that is, P is equal to delta W by delta T. That is equal to IV delta T by delta T. Both numerator and denominator delta T get cancel. We get P is equal to IV. SI unit of power is watt or joules per second. Next, Kirchhoff's rules. 1. Junction rule or Kirchhoff's current law. It states that, at any junction of circuit, the sum of the currents entering the junction is equal to the sum of currents leaving the junction. That is, at the junction, total current entering is equal to total current leaving. Let I1 and I2 are entering currents. I3 and I4 are leaving currents, as shown in figure. Therefore, I1 plus I2 plus minus I3 plus minus I4 is equal to 0. That is, I1 plus I2 minus I3 minus I4 is equal to 0. On equating we get I1 plus I2 is equal to I3 plus I4. The significance of Kirchhoff's current law is that it explains the law of conservation of charges. According to junction rule, there is no accumulation of charges at the junction. Next. 2. Loop rule or Kirchhoff's voltage law. It states that the algebraic sum of changes in the potential around any closed loop involving resistors and cells is 0. Applying Kirchhoff's loop rule to the loop ABCDA, we get minus IR1 minus IR2 plus E is equal to 0. Therefore, summation of IR is equal to 0. Here, if the current moves from low to high, then the EMF, E, source is signed positive because of the energy charging at the EMF source. Likewise, if the current moves from high to low voltage, plus to minus, then the source of EMF, E, is signed negative because of the emptying of energy at the EMF source. In this solution, the direction of the current is the same as the direction of clockwise rotation. The significance of Kirchhoff's voltage law is it explains the law of conservation of energy. Next. Applications of Kirchhoff's law. 1. Kirchhoff's laws are applicable to analyze any circuit regardless of the composition and structure of it. Some of its applications include to find the unknown resistances, impedances, voltages, and currents, direction as well as value. 3. In a branched circuit, currents passing each branch are determined by applying KCL at every junction and KVL in every loop. 4. In a looped circuit, the current passing each independent loop is determined by applying KVL for each loop and calculating the currents in any resistance of the circuit. Next. Limitations of Kirchhoff's law. 1. Kirchhoff's laws are limited in their applicability. They are valid for all cases in which total electric charge is constant in the region into consideration. Essentially, this is always true, so long as the law is applied for a specific point. Over a region, however, charge density may not be constant. Because the charge is conserved, the only way this is possible is if there is a flow of charge across the boundary of the region. This flow would result in current, thus violating Kirchhoff's laws. 2. Another limitation is that it works under the assumption that there is no fluctuating magnetic field in the closed loop. Electric fields and EMF could be induced, which causes Kirchhoff's laws to break in the presence of a variable magnetic field. Next. Wheatstone bridge. It is an electrical network in which 4 resistors are connected in the form of quadrilateral. A cell is connected between the diagonally opposite points. A galvanometer is connected between other 2 opposite points as shown. From the figure, AC line is source arm, where cell is connected. BD line is galvanometer arm. IG is current through galvanometer for balanced bridge. Here, IG is equal to 0. Then galvanometer shows null deflection. Let's derive expression to balance condition of bridge for null deflection of galvanometer. From figure, consider a Wheatstone bridge. Let R1, R2, R3 and R4 are 4 resistances. I1, I2, I3 and I4 are the branch currents. IG is current through galvanometer. G is resistance of galvanometer. For null deflection, IG is equal to 0. Now applying Kirchhoff junction rule at B and D, then I2 is equal to I4. and I1 is equal to I3. Applying Kirchhoff's loop rule to the closed loop ADBA. That is, minus I1 R1 plus 0 into G plus I2 R2 is equal to 0. Because IG is equal to 0. Therefore, minus I1 R1 plus I2 R2 is equal to 0. This can write as I1 R1 is equal to I2 R2. Equating above equation. I1 by I2 is equal to R2 by R1. Mark as equation 1. For closed loop CBDC. I4 R4 minus 0 into G minus I3 R3 is equal to 0. Because IG is equal to 0. Therefore, we get I3 R3 is equal to I4 R4. Equating above equation. I3 by I4 is equal to R4 by R3. But I3 is equal to I1 and I4 is equal to I2. Therefore, above equation can written as I1 by I2 is equal to R4 by R3. Mark as equation 2. From equation 1 and 2, we get R2 by R1 is equal to R4 by R3. This is the balance condition of Wheatstone bridge. Note: we have R2 by R1 is equal to R4 by R3. If R4 is unknown, then R4 is equal to R2 by R1 into R3. Therefore, R4 can be found. Wheatstone bridge is used to find the unknown resistance. This ends current electricity chapter. In the next video we see some problems on current electricity. Don't forget to subscribe the channel for more updates.